Hi guys, today we're covering Transformers and TurtleGPT. So before we start on those specific topics, let's talk a little bit about how do you actually represent words or tokens, we'll see later, in neural networks. So a lot of times, I mean, let's just assume for now, because I'm going to show you kind of an initial way that this gets treated. But for now, let's just kind of take maybe the most obvious way of doing it. And that would be basically to say that assume we have a vocabulary that's like 10,000 separate words. You can get pretty far in a language with 10,000 words. The one hot encoding method would be basically to say this. If I wanted to encode, say, a sentence, what I would do is I would have a vector that's 10,000 it's 10,000 booleans. Basically, it's a bitmap of 10,000 booleans. And if the word is present in the sentence, I turn on that specific word. So the word, for instance, boy, might be like the 1565 offset into that bit index. Okay, so we have 10,000. These are big vectors, but we turn on the words that are present in a sentence. Or if we're just going to be doing one word at a time, we just turn on that one word. Okay, so already this seems like not a good idea, and it isn't. And we'll see how we get beyond that right now, right here. So an n-length vector with n number of words. Okay, so 10,000. It's a bitmap vector, just on and offs of zeros and ones. That's 10,000 long. So the sentence. Dog bites boy would turn on three of those positions for those three different words, and of course, dog bites boy then would get the exact same encoding as the boy bites dog, but these of course have separate meanings. But let's just kind of go with this bag of words representation for the time being. Now, all the words are, everything's just like, it's like this 10,000, it's like a vector space that's 10,000 dimensions. So all the words are the same distance from each other. Okay. They're all the same distance from each other, but, and there's no ability to generalize between words. So this feels bad, but let's just go with it for now. Now, a better way of doing it though, is to use embeddings. So we basically say, no, we're going to try to scrunch down words into vectors that are, say, over a dimension space of, say, 300. So each word will wind up being a vector in that reduced dimension space of 300 words. And then hopefully the distances will respect in some sense the meanings of the words. Okay, so this is the essential idea behind word to vec. And let me just quickly show you how you would go about training something like that. Now, we're not going to use this for our embeddings. We're going to get embeddings for free off of the GPT and off of the Transformer network is going to actually let us calculate this as part of the learning process. But let's just do this to kind of just get an intuition about how this kind of happens in a very simple case. But again, this is a throwaway. We're just going to kind of look at this and then we're going to discard it. So one idea is the following. That is that we have that one hot vector there of the 10,000 positions. And let's say this is the correspond to the word ants or, ants. And then what we have here is we have 300 separate neurons that are basically, that basically are a linear, they're a linear combination. And then a sigmoid. It's a linear combination of this 10,000 values. Okay, so only one is going to get turned on at a time, but then that will impart a certain amount of there's a certain weight that's going to go in there, so it's going to have a certain effect on each of these nodes in the hidden layer. Okay, now notice 300, and that's like the dimension. That's the dimension size that we're going to have. So let's just go with this. So let's say that we have ants, and then let's look at a corpus. We have this huge corpus that says something like ants like sugar, ants desire sugar, and so those are sentences that are in there that are observable sentences in this giant corpus of material that we're going to feed in. So what that means then is it means the following. So what we wind up doing is we wind up trying to basically say, let's train this network, this embedding network here, to try to predict what's the next word that's gonna come along. So ants. Okay, what's the likely next word that might come along? Well, like maybe, or desire, or eat, something like that. So the point is that what we're doing is we're doing a connection between ants and then whatever the probability that okay, so we can look at over all the different words that might follow ants, and then we can basically put those in here as a signal. And what that will wind up doing is it's what we're doing is we're saying, well, if we just have this word here, let's predict what are the possible next words. Okay, in that. So the point is that if you do this, if you actually do this huge training, and you grind this over a huge training, what you wind up getting is this thing at the end here. You get this transformation that will take you from something of dimension 10,000 down to, this kind of so you just take a point for each one of these nodes in the hidden layer, and so there's going to be 300 of that. So what you wind up doing is you wind up getting a vector here that collapses the 10,000 and then with the one hot knot, and then it collapses that down into 300. Okay, so it's a big linear transformation of values of values that were trained on this next word prediction. Okay, so this is kind of what word2vec did, right? I'm kind of just like glossing over it a bit, but that's kind of what word2vec did. So the important point is this: is that once you pull that out, then what you've done is you've formed an embedding space, right? And then in this embedding space, right, so we have basically, what are the dimensions of the embedding space? It's n times d network. N is the 10,000 and d is 300, right? So it's kind of that's what the word embeddings are. That's what comes out of that training process. And the interesting thing is that when you start looking at the distance between the words, you'll find that words like bad and awful kind of cluster close together. So we're getting this kind of notion of the words kind of close coming in on they're kind of getting closer together based on their meanings. Okay, and then as far as distance, what does close mean? Well, there's different ways to calculate distance. You can do dot product, cosine, Manhattan, or Euclidean. Okay, so dot product is a real cheap way of doing it. So we probably go with dot product most of the time. Okay, so that just gives you kind of an intuition of, so what does this mean? This means that if I have the sentence, dog bites boy, what that's going to wind up being, okay, dog. How do we represent dog? Dog is going to be 300 real values, okay, that we picked up from the embedding matrix. And that's so we have 300 values there. And then I say bytes, that's another 300 values. And then I say dog bites boy, and that's another 300. Okay, so those in order, those boom, 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 that's a total of 900 real values that come across, and that is the input into your neural network that represents the sentence dog bites boy. Okay, so right, good. So that's going to be important now. So we have a way now to basically start talking, since we had this embedding we've kind of trained up these embeddings. Now we have a way to talk about stringing together sequences of words. Okay, so sequences. How do we deal with sequences? Okay, so neural networks, we can kind of do it in a very general way. We can kind of think about it in a very, very general way. Scalars, that's just a single. So what are the things that can map to one another in a big neural network? Well, we can have we can have a big vector of values that then get trained to map to a single scalar, like deciding whether or not something is like in logistic function, like saying, okay, does this whole thing represent the value the 7? Okay, that's mapping to a single scalar, which is going to be between 0 and 1. What's the probability that this whole thing represented a 7 digit? Okay, so that's a mapping from vectors to scalars, and then we might have a mapping from vectors to vectors, right? So it can, so for example, in this deep learning, when we're mapping from the input layer to a hidden layer 1 to hidden layer 2 to hidden layer 3, those are all vector to vector mappings. Okay, so then but the problem with sentences is that those are variable length, right? So they're a sequence. So now how do we deal with sequences, right? How do we deal with sequences? Um, and okay, and then variable length. How do we? So a lot of things in the world are variable length. Like stock price is variable because it's like, well, not all stocks have been around the same amount of time, right? So you have, okay, words in a sentence, right? Cameras in a self-driving vehicle, right? Right. There's a lot. This is very naturally occurring. So variable length inputs as sequences. Abstractly, we have scalars, factors, and sequences as the fundamental objects, right? Okay. So now, what are we going to do about this? We've got two options essentially. We can do an RNN, which is a recursive neural network, which basically says that, well, I have this sequence. I'm going to feed the first element of the sequence, and that's going to then go and it's going to set the state in some it's going to set the state of say the state of agitation, if you will, in some state variable of a neural net. And then on the next, when the next word comes in, I'm going to take that whatever that state is plus the next token coming in, and I'm going to use that to kind of redetermine another state, right? And I'm going to do this, and so the state is always being affected, right? So this is kind of the very sophisticated way of doing it. It kind of stretches things out in time, but you get these kind of hidden. You have to get this vanishing or this exploding gradient problem. There's a lot of problems associated with that. LSTMs were a real innovation in terms of kind of controlling this and having it so that you kind of can manage like you can manage how much the next input affects the state, what can last in the state. It's very complicated. It's very deep. But there's another easier option, and this is the option that was taken. This is actually one of the reasons why it's called attention is all you need, because it says, okay, get rid of the recurrence. Forget it. We're not going to do recurrence. What we're going to do is we're going to say, okay, you've got like some sequence. Good. We've got a context window, essentially. We have a very, very wide vector. So we can accommodate many different sequences, but there is a cutoff. It's finite. But we just decide this is the fixed context window size. You got a sequence, well, we better hope it fits in there. If it doesn't, we can truncate things off of it. If what you're putting in is smaller, we'll put the thing that's smaller in and then pad it with a bunch of empties. Okay, but we're just gonna, it's kind of a very direct way to handle sequences. Just say, well, we don't have sequences. We just have a really long vector that we only partially fill up, or if we overfill, we have to leave something off. Okay, that's it. That's nice. Okay, so we get this context window. All right, and this is what's going to be. This is what happens in the with transformers. Okay, so now the attention is all you need paper. So this 2017. This is a very very influential paper coming out of Google DeepMind. So Google was it came out of there. It did not come out of academia per se. It didn't come out of the universities. But it came out of Google DeepMind. Okay, so it was originally applied to machine translation, and we're going to kind of it's part of your readings. It's good. It's really a nice. If you want to be in there, I mean, it's like have you read Attention is All You need. It's kind of like, well, you should have. If you want to be an expert in this kind of stuff. It's in our readings, but we're going to kind of gloss over it quickly here. The point is, it's a bit more complicated than what we need. So what happens here, and they just kind of describe it, it's going to be doing an encoder decoder type strategy. So what the input was French, and the output was English. The output here is English. The input is a French word. So a French sentence. So the sentence comes in, and you can see this thing. Think of the width of this thing as the width of the context of the context window right here. The width of this guy is the context window. Now. We do have a separate embedding that happens kind of independently. That happens on a token by token basis. So that's if you want to see this as just kind of this very wide. Well, the embeddings kind of happen as a separate piece. The embeddings are the number of tokens in the vocabulary, and across the dimension. So in this case, instead of 300, we're going to use 512. Okay, 512 is what it's going to be. So what happens then is that we're using, it's key to know this, that we're using the same embeddings for each token, right? So if we have what is the context window width here is 350, so we can put 350 tokens in, a French sentence of 350 tokens, and then what's going to plop out the other end is going to basically be. We'll talk about that in a second about how it actually will. Like if I say, okay, je t'aime, which that means I love you in French, then we better have I love you pop out the other side. And we'll talk about how that happens in a second here. That's part of the decoding. So what happens basically is that the input comes in, then there's this Fourier-like transformation. This is actually learned in GPT later, but it's a Fourier-like transformation that basically does positional encoding. So what this means, it means if I have the actual input into the transformer network, if I have dog bites boy, well, the dog will get like a little bit of a Fourier transform, a little waveform, because it's in position. It's in the first position. Bites will get a waveform because it's in the second position, and then a boy will get get something added to it as a transformation because it's in the third position. So then, what that means, then it means that if you look at dog bites boy and what goes into the network, because of this positional encoding, that will be different than boy bites dog. Although the bites, because it's in the second position in both, will be the same. Okay, so that's something. So the point is that what this is doing, this is making it so that the position of the word in the sentence actually matters. Okay, so it's something to know. That's so positional encoding is critical for this all to work. There's a lot of pieces in this whole thing that are kind of critical. You need them to have them in there for the thing to work, and positional encoding is one of them. Okay, so each coding or decoding block consists of attention, normalization, and feed-forward numbers. Okay, we're going to kind of deal with this in a more kind of in the GPT case. But let's talk a little bit about more what's going on here. So what's happening is the input je t'aime is coming in, and then what it's doing is it's getting encoded, and then this part here is then doing the decoding into English. So je becomes I, and then I don't know. Well, So, but how is the decoding really happening? Now, the decoding is happening as what's called it's happening auto. It's an auto regression. Okay, and so we'll talk a little bit more about what that means when we look at GPT. But what it means that what we do is we start out with just the only thing we have coming in is je t'aime. That sets some kind of context. Okay, set some type of internal state, right? And then what that will do is that will then drive the production of the first word, the very first word coming out. And the softmax is over all the possible tokens of the language, and it will find that the most likely, when this whole thing washes through, the most likely one is I. Okay. Then what it will do is it will use the state here plus I, and then it will push that through again, right? So this is what's autoregressive. So then it says I with the state of whatever came from the French, je t'aime, and then it pushes it through, and then it says, the next word must be love. Okay, fine. And then what it does, it's going to push it again through again now with whatever state that came from je t'aime coming in, plus I love. And then what it's going to do, it's going to push it all the way through here, and then it's going to be you. Okay, so what's doing is, like, say, at first it's pushing through I plus the state from the je t'aime. Then it's pushing through the guesses love. Then it's saying, and then it pushes through I love. Okay, and then it guesses you, and then maybe the next thing it guesses is that period, done, finished. That was the sentence. It's over. Okay, so that's kind of the part of what you'll see more when we do to GPT, the auto regression. Okay, so what is GPT though? Because GPT is kind of what is like the star of the show here. So GPT is actually just this part here. It's just the decoder. Okay, it's not. So it's the original paper was doing full translation, which is a bit deeper, more, and what. Okay, we'll get into the blocks when we look at GPT. So this is GPT. Okay, so GPT is just this half. I wonder if I should actually, at this point here, maybe I should get my pen out here, turn on the pen. Okay, so this essentially, with some modifications, this becomes GPT, the decoding side of things. So, what do we have here? Okay, so this is the structure of it. So what we have here is we have the input comes in. All right, so the input is like your prompt. Okay, the input. So let's talk. We have to talk about training time. We have to talk about inference time. But let's just to keep it kind of let's just to keep it kind of clear or more intuitive. Let's talk first about inference time. Let's assume we've done all the training. Um, the input that comes in here might be like I love, and that's just, so there are two tokens that come in. So we'll just assume that words are tokens here. And so what it will do is it will take I and it will run that through the embedding. It will take love and run that through embedding. And then so it'll generate a vector for I and a vector for love. And then what it will do is it will then shade, it'll make a little bit of a change, kind of jostle around the uh, the encoding for I, the 300 or 200, 512 real values for I. It'll jostle that based on the fact that it's in position 1. Okay. And then it'll do the same thing with love because it's in position 2. So it's getting a little shade there. Then it'll do a dropout just so that we're not getting overfitting. So it'll basically just kind of zap a couple of neurons, just kind of drop them out, just to kind of get some little more robustness. And then what it will do is it will throw that into a transformer block, and then to another transformer block, and then to another transformer block. And these are all like the width. These transformer blocks are the width of the context window. So it's just going to boosh, 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 kind of doing this. God only knows what's going on in the transformer block. It'll take all that. It'll do a normalization so that the numbers aren't getting a normalization. What is a normalization? Normalization just means that you kind of bring everything stays relative to each other the same, but it just kind of tones it down or amps it up, whatever. It's just kind of putting it in so that the magnitude of the total is kind of reasonable. That's what these normalizations are doing. Okay, then it's going to put it through a final linear layer. All right, and then it's going to do a softmax. And then the softmax will be over the whole size of the tokens. And then what it will decide, when it pushes all that through, it will decide what is the next token. And the next token is you. Okay, now down here in each of these these are each of the transformer blocks. So what is the transformer block? Again, doing some normalization, doing some linear stuff. Now, what it does, it's interesting. What it does, it will take the words, the encoding of each of the encoders, so the 512, and it'll split that up into separate heads. Okay, and the reason why it does split up into separate heads is because those separate heads are can kind of cover different kind of areas, or they're all independent heads. They're kind of just like going to be doing a little inference over this little part of it, and then another type of inference over this part of it. So under the hood, God only knows what they're doing, but they're separating it out. So they're doing separate analyses over these. But what they're going to do is, this is really where, and we're going to focus in on this. This right here is the real spot where what's happening are, all right, so I take the words I love, okay, good. And all right, I is like this huge encoding. I say, okay, I'm going to take a little piece of that and a little piece of you, and those are the first head. And then there's the second head, the third head, etc. But we'll take those first head, right? And then what I've circled here, it's going to take those and it's going to say, okay, so now we'll call this a word. We'll call this a word right here. Now those things are going to rub up against one another. They're going to send messages to each other, okay? They're going to influence each other, right, in some kind of strange way. And they're going to kind of like jostle one another, all right? That's the core of it. The core inside the transformer block. That's the core notion of this attention. So they're attending to one another. All right. And then what'll happen is then we'll kind of put them all back together again. Right. So we kind of do this concat operator. We put them all together again, send them through a linear layer, do a dropout, normalize, put it through another linear layer, and then apply the GELU, which is like a ReLU, but it's got like it's got some nicer things because it has a little bit of a grading to play with, rather than as you'll see in recitation 1, ReLU got some problems. It's fast though. It's good for vision stuff. But anyways, it just wasn't determined empirically that the GELU is a little is more effective, and it can be computed. There's an approximation to it, so it can be computed fairly quickly. Anyways, it goes through that linear and then drop out, and then finally all the output is then kind of moved on to the next transformer block, and these blocks just stack. Okay, right. Okay, so let's see here. So okay, it's kind of repeating. The GPT is a decoder only transformer. Right. Okay. Well, GPT-3 was there's a lot of parameters in this thing, right? There's a lot of weights that are getting involved here. GPT-3 was 175 billion. So, and what it's doing is it's training on the next token. So what it's trying to do is it's trying. So I was talking about inference there. So let's talk about the training. So the way the training works is that you go out to a corpus and you get a sentence and say, okay, great. All right, I see. Well, okay. You look and see. I really like fresh. Okay. Now, most of the time when it says I really like fresh, the next word is fish, right? I really like fresh fish. I think it's tasty. Okay. Or, well, it's going to be like fresh salad. I don't know. Whatever. But it's not likely to, the next word is not likely to be castle. How often does that happen? Probably not at all, right? So over all the words of the language, there are going to be some words where there's some likelihood that the word that follows is next. So that's what you're training on. You're going into, and this is why it's non-supervised, because you just have to go out and look at sentences and say, oh, well, there's a sentence, and what's the most likely next, and then that'll be part of my corpus. I can train on that, whatever that next word was in that particular sentence. I can train on that. I can train my GPT on that to predict that word, because that word is something that actually happened in nature, right? And there might be some other, that same exact prompt might actually lead to other words. So, just kind of train it all, and we'll start representing the probability distribution of what is the next word in the corpus. Okay, right. So that's how. So what happens then is that when the thing is completely untrained, it'll go through and it'll just say, the final thing coming out of here is a softmax. And if it says, like, when it's not even training, it says, I love. Okay, I don't know. I'm not trained yet, so I love castle. I love you. I love billboard. Those are all equally likely because it's just starting out with this training. But when we look at when we're actually doing the training corpus, U gets a good signal, because that we see that as happening out there in the actual data. So that what that does is then that sends back a that there's it's going to do basically this is all really just a multi-layer perceptron. It's going to wash back the gradient. It's going to calculate what the gradient is to kind of move it toward that correct answer, right? So it's going to so that's how the training is going to work. So it's training on next token prediction. During inference, the prompt supplied will auto-regress until a special EOS. Okay, yeah. So now what's interesting about training is we can do this in batches, so we can train a whole bunch of these things in parallel. Because if I take a sentence from the corpus. Good. That's a giant vector, right? Right. If the sentence is, like, say, 10 words long, that's going to be 10 times the D model size. So 10 times, say, 256. That's how many values there are there. But if we just look at the point of, like, these are the tokens. I have, there's the token size as well. So there's all the distinct number of tokens in there. So I look at my corpus and it has this long sentence, and I say, okay, that's token number this. I tokenize it. Right? And I take that down, and I just have a whole sequence of tokens, right? And then I shift them by 1, right? And I then say, that's the Y. I shift it by 1 into the future. That then becomes what I train on. That's because what it's basically saying is saying, okay, well, if I'm in this position, I should predict what the next word would be, because that's what it would be, shifted by 1. Right? So that's actually what you put in to do the training. So when you do a training, when you do an actual training problem, it's simultaneously training on many of word prediction problems, right? If the sequence that you're putting in, well, whatever it is, the context window size minus 1, that's how many examples you're training on, because you're just doing the shift by 1 and it's doing the prediction up. So that's really nice in that way. And then you batch things up and there's even more going on because you can have all the things batched up. So you're really keeping that GPU busy as it's pushing through. So it does the forward. And then when it's doing the forward, it's like all these links have gradients that are going to then be they're all being run with being prepared to calculate a gradient, and then we do a back, and that calculates the full gradient, and then we take whatever that full gradient is over all the links, and we basically take the learning rate and we go in and we zap the weights based on that. So the weights get moved more toward getting it better. Okay, getting closer to predicting the next word. Right. Okay, and we do that, and we burn millions of dollars if it's it's a lot of burn in there, but it will converge. Right, the loss will get lower and lower and lower the aggregate measure of loss will get lower and lower. Right. Okay. So let's try this. Seems like I turn off the pen there. So let's go on. Let's go a little bit deeper into what's really going on inside the transformer block. Okay. So here's kind of how it works, and we have the code for this. So we'll later on we'll look at the code that does this. But what we have here is and again, let's just forget about heads for the time being. Let's just say that we just have that they're all separate. So basically, we break it down into 3 pieces. There's each word has a query, which basically says, "Oh, this is what hey, every word, all of you words down there that can match this query, talk to me." Okay, so it's kind of like it's opening up its ear, saying, "Here, I'm asking for influence from all you other words on this particular channel, if you will." Okay, then each word is saying, "I am who I am, and I'm gonna send out me on one particular channel." So if one word says, "Here's my query, talk to me on this channel," and another word says, "Well, I'm going to talk to him on that channel." So there's a perfect match there of that channel. That means that me as a word am going to have a lot of influence on that other word. Okay, I'm going to have a lot of influence on that other word, and that my influence is based on what is my value. This is the actual value that I'm going to contribute. Okay, this is the value that I'm going to contribute, and then by doing that, I'm going to rub against that other word. Okay, so this is a little bit. Basically, what we do is we do this via dot products. Okay, and then we'll see that we're going to do a softmax in there as well. But let's look at the actual. An actual example here. Okay, so this is a D model of 3. Okay, and we have, and in this case here, we're going to let both words influence each other. Now, in a decoder architecture, you actually mask this, so only the earlier words influence the passwords. The passwords don't influence the earlier words. Just it's called causal attention because it's moving forward in time. But in this case here, just to kind of get the example to kind of work. We're going to do where they both influence each other, which is what actually happens in the encoding in like the other side of the transformer network, where it lets everything kind of mingle together. So let's just look at that thing. So we have angry, which is represented by like a little angry symbol there, and then we have a cat, which is just like, there it is. That's nice kind of black cat. So the parameters here that are in blue are trainable. Okay, these are the ones that are actually they're being used now. They're being used. We're going to push forward with this thing, but remember, on the backward, these can have a gradient applied to them, and they can then be shifted based on training. Okay, so angry comes in. There it is. It's represented as a D model of 1.2. That's what it is right there. And then what happens is that it goes through there it is right there. And based on that, what we're going to do is we're going to do a matrix multiplication here. So we have a if you look at the shapes of these things, what will come out of that is a, I might be doing some transposes here, but basically what happens is we're going to push this angry through this matrix here, and we're going to build the query for angry. So this is the channel that angry is listening on. It's like saying, okay, if you want to talk to me on this channel. Same thing with cat. Cat also gets pushed through there, and using these parameters here, gets pushed through. And so we have two vectors there, one representing the query for angry, the other one for cat. The same thing happens with the keys here. So we got the key for angry and the key for cat. And then what happens is, and then here in terms of the values, I'm just going to keep it simple. I'm just going to have the identity matrix. So there's nothing going on there. But that's not true in practice. I mean, that actually also is something that's learned. So in other words, we just copy those up to there. Okay, so what we do then is we say, okay, we calculate a matrix then. This is kind of the influence matrix, which is going to be the query times the key transposed. Okay, so what this is showing, if you look at this, if you look at the main diagonal here, what this means, it means that, well, for the most part, angry is feeding on itself, and cat is feeding on itself. But notice here that there's a little bit of like they're talking to each other. These two different words are talking to each other. Now we push this through a softmax to basically normalize it. Okay, so here's the softmax, right? Because what are you gonna do with a number like 14.4? That's crazy. That's a crazy number. Okay, make a softmax. All right, so we're gonna bring it down. All right, so these kind of represent almost like probabilities, or they represent probabilities. Okay, so there's the softmax. And then the actual value is going to go through that softmax. So this is actually right here what we're going to get out. And you can see that all the shapes work out here. And there's the output. The calculation basically comes up to here. We wind up calculating a delta. So this is the amount of influence that we're going to apply to angry. And this is the amount of influence that we're going to apply to cat through this whole process here. Now this is so critical. Notice here we have this dark line right here, which is called the residual connection, which just does a copy up. It just copies up 1.2, 3.2, the exact angry. So it's completely bypassing all this stuff, all this crazy stuff, and just washing through angry goes to angry goes to angry. Okay, right. It's just washing it through on the residual. But notice what's happening here. We calculate a delta, and so that delta then actually delta is much smaller though than these numbers here. But what this does is it slaps whiskers on that angry symbol, and it puts a scowl on the face of that cat. All right. So the words are rubbing against one another. All right. That's on the inference side. On the training side, well, depending on what loss we had, we're going to push this back, or we're going to change the way this is actually being calculated. Right, the way it's actually being put together, right? So this is the heart of it. This is the belly of the beast, as it were. Okay, this is it in code. All right, so in recitation, you're going to have to like play around with this a little bit. You can see some of this code, then what if we look at we think about like the interaction. So in the case of non-causal attention, just kind of the general case of attention. The amount of interactions we get, if we just have one word, it says cat, there's not going to interfere. Angry cat has 4 interactions. Cat feeding on cat, anger feeding on anger pushing itself to cat, and cat pushing itself to anger. Angry cat behavior is going to have 9, so it's going up as a square. Okay, it's going up as a square in the number of tokens in the sentence. That's how much interaction there is in this. That's the size of that matrix. Okay, so what are the dimensions of angry cat? Angry stray cat behavior must never be rewarded. I'm not sure if I agree with that though. I mean, let's go easy. That's going to be, okay, 1, 2, 3, 4, 5, 6, 7, 8. That's going to be there's going to be 64, right? There's going to be 8 times 8, 8 squared interactions potentially. Again, when we're doing decoding, what will happen is we'll clip off the ones that are the things that happen in the future and influence stuff in the past. We just We basically, there's a trick in softmax, so you can just kind of like take those down to, you know, negative infinity on the logits, and then we turn it to softmax, and then turn it all to zeros. Okay, so the angry cat stray behavior. There's actually only 10 interactions there. So you do just the kind of the quick calculation there. Okay, so now we're gonna now that we've covered that, now we're gonna nose down into some code that actually shows this. We're gonna actually go into this TurtleGPT, and we're gonna kind of see it in a wide sense of kind of actually how is this being achieved. Okay, so let's do that. Okay, guys. Right. So now we're going to look at this TurtleGPT. So, right. So TurtleGPT, as you see right here, it fits into, it's in this directory here, TurtleGPT. And there's a corpora subdirectory. And inside that, let's just look at this at first. Okay, so this is what we're going to actually train over. So I just want to start out with that. So these are a bunch of sentences that have to do, like, okay, so for instance, the old cat bites the dog, the rich cat loves a rich rabbit. So we have these different animals, and we have different adjectives, etc. So this was all, if you're curious, if you want to generate your own, you can go here and you can actually generate the corpus, but let's get back here to the actual corpus. Okay, so what's going to happen here is we'll actually watch it run here, and it's going to start kind of converging in on this. But let's go. This is the corpus. This is the main corpus, and then here are some prompts that we actually use. That we'll see, like the clean rabbit admires the frog. Period. The frog. Then what? Okay. So these are just the prompts that will be thrown into training. These will be thrown into. These will be used to kind of show the progress during the training. These are the prompts we're going to be using for that. Okay, so let's look at the code itself. And first off, let's just maybe we just start out here with just the model here. So no, this right here actually. I'm kind of surprised that showed. Here's the model, not model.pt, but model.py. So first off, this code is derivative of Andrei Karpathy's min-GPT, also with significant influence from Umar Jamil's implementation of attention is all you need. So those are kind of what inform this. But what I'm trying to do is I'm trying to get this, even trying to move it, maybe this afternoon I'll make some more moves toward it, but I'm trying to get this kind of an ASAP, as simple as possible, but no simpler implementation. So I'm not looking for kind of production quality here in terms of something that you could actually use in some kind of production system. I'm more interested in just kind of making it really as simple as we can possibly make it. The simpler, the better. But we don't want to lose it. We don't want to lose if you make it too simple, then poof, it doesn't work anymore. So this is the main model. So let's just go over this because this will kind of show you that kind of correspondence between this and the lecture. So it's a class. It's called TurtleGPT. It's using Torch's module, so it's inheriting a lot from Torch. As we'll see later, then the device, it better be CUDA, because we want to get the performance here. But this is actually the important thing here. We have this structure of the input embedding, right? The positional encoding, the dropout, and then the layers, which are a set of transformer blocks. And the number, in the initializer here, it'll tell you how many layers to build. But basically what that is, that this is kind of setting everything up. This is the init. This is initializing the weights. And this is configuring this atom, this optimizer. This is the forward. So this is actually was taking your inputs and moving all the way forward to get out the logits that come off of the in the final step of the process. This generate here, that's just for doing kind of inference. So we're not doing training. Notice here, this right here, this When generate, that's just this. We're just doing this during inference. It basically says that don't calculate the gradient because we're not going to use it anyways. So don't calculate it. That's what that decorator says. All right, now this is the belly of the beast here. This is the transformer block, and inside here, the important thing is we have the causal self-attention part, and then that is down here, and this is doing the message passing. This is the queries, keys, and values that we just talked about. So this is doing all that. This is the forward for it, and yeah. So that's it. That's the model. So it's really short, you know. So I feel like I can make it a little simpler somehow. Like maybe I just don't want it to like. I mean, one of the things that complicates it is the fact that it's doing batches, but it's probably best to keep the batching in. But I still think that there's some places where I can kind of at least clarify it. Kind of. Anyways, right. Okay. So how's this used? Now we go to the main, and this is probably where you're going to spend most of your time. So right. So there are these different. This is kind of you might say, oh well, why don't you? You know, this is kind of minimal. I'm trying to do everything minimalistically here. Usage. So what are we doing when we run this thing? Are we doing inference, pre-training, or SFT? Which will be that'll be next week. So don't worry about that. Or the week after next. That's the fine tuning. Okay, supervised fine tuning. But anyways, in this case here, we're doing the pre-training. So right now we're actually going to train it. And then what setup are we going to use? So we have different setups. We have this GigaTurtle, which has a window size. That's the context window size of 128, 8 layers, 8 heads. The D model is 256. And if you think about it, like this always has to be divisible. The D model has to be divisible by the number of heads because we don't want to have fractional heads, and so 8 indeed divides into 256. And this is the batch size. So this is kind of what we're piling into the GPU. So we have GigaTurtle, we have Big Turtle, we have Michelangelo, Baby Turtle, and Nano Turtle. So look at Nano Turtle. Nano Turtle is really only one layer, one head. So there's no heads at all. There's just one head. Four real values represent a word. So this thing is really pretty small. The little Nano Turtle is really small. So, but let's run right now with GigaTurtle. There's our learning rate. That's okay. Now the vocab size is basically what size vocabulary do we want? So not 10,000, not 10,000. How many tokens are there? And then we'll see here this, and we're going to cover it in a little more detail later in the lecture of this byte pair encoding. But we're going to just fix it. We're going to say we want 100, the vocabulary size to be 100. Okay. Here's the training set. So the training set then goes to this thing called a corpus here. Let's look at the corpus. So the corpus is basically, it digs down into the corpus file. So it digs down into that stories. So, but what it does here is it will give you like an item from it. So it'll like kind of randomly, given a start somewhere into the corpus, it'll pull off from that. It'll pull off a encoding in the token encoding of X and of Y. And notice here that X is just a one offset, or Y is one offset from X. So this is when I was talking about that training thing where it's just we take something from the corpus and we shift it by 1, and that gives us kind of how we match up and we can do the training. That's exactly what's happening here. The encoding is using our token encoding. So we'll get a little bit better sense of this, but let's go back into main here. So it really is it's kind of a short amount of code. I'm trying to look to make it shorter. Always looking to make it shorter here. Okay. So if we're doing training here, then it's just going to go into the trainer. And then if we look at the trainer here, that's another class. Right, it takes in all these kind of parameterizations. It sets up the optimizer. And then it just does it in the loop, calculating the loss and doing the, calculating the gradient and then applying the gradient. And then right here, every fifth time it does it, it'll then print out, it'll show us kind of how far it's getting. Okay, so let's just run it so that we can see it. But maybe I'll breakpoint it in the corpus here. So there's one little thing I'm going to breakpoint in 2 spots. I want to show you guys 2 things as this thing runs here. So the first thing I want to show you is in the model. I want to, I want to just breakpoint it there, and then I want to go into the corpus. Do I want to do this in the corpus, or do I want to? No, I think this is good enough. Let's just run from here. Okay, so let's get back to main, and let's let it rip. Okay, so debug. So let it rip. Okay. I think there's a little bit of a problem here. I think I was running it in the background here for some reason. I'm going to see this model.pt here. I'm going to get rid of that because I don't want, I want it to start out completely fresh. So, okay. So now we're going to restart it. We're going to restart main. Okay, we're going to debug main. And then what we'll see here is we'll see, okay, so here we are. So self.device, let's first just verify, and this better work. Good, it's CUDA here. So for some reason, I lose this sometimes and I have to reinstall stuff. So like for instance, yesterday it wasn't running, it was running, it said here instead it said CPU. And I was just like, well, why I got this to work before? And then I had to reinstall some stuff. Something got shifted. But okay, now we do know we're using the GPU. So we're gonna, you know, now let's just carry on from there. So boom, let's let it run. Let's let it rip here. So okay, and then maybe here. So look right here. This is kind of nice. So even GigaTurtle is only 6.4 million parameters. So it's not even a billion parameter model. But of course, this is a pretty small corpus. But I mean, NanoTurtle is just really puny. Okay, so let's look what's going on here. All right, so we're doing the iterations here. So okay, so here's the prompt that comes into the system. This is like completely fresh system, completely fresh weights, just random weights. All right. The prompt that comes in is the clean rabbit admires the frog. The frog, and then there's not, it's just like empty. It's not giving us anything. Saving the model. So look at the losses. Wow, look, it's really popping around there, 5.2. So really high loss. But now look, now we've done a little bit of training. So we've gone through, we pushed through, we can look in the training, see how many times we ran through the training. But now we say, when we give it the prompt, the old rabbit hits the rabbit, the dirty, and then the completion of and then a frog in there. Okay, so it's still gibberish. Okay, so we keep on running here, and look at this. So okay, so now let's come up to date and just see this thing running in real time here. Okay, the loss is really, so look at that. So I think it's actually kind of, let's go back to here. In this case, the old rabbit hits the rabbit, the dirty cat, the cat, the cat, the cat. Okay, still gibberish, but a little less gibberish. So let's go down here and see how it's kind of doing here. Okay. All right, now, the old rabbit hits the rabbit. The dirty dog loves the dog. The old dog loves the dog. The dog loves the dog. The rabbit loves the dog, etc. It's kind of going on. Okay. So the loss is still going down. So let's just let this kind of run around here. So what's remarkable about this, actually, as you'll see, and maybe we'll actually kind of witness it here. What's remarkable is that it's going to actually get to a point where if you give it a prompt, like for instance, I give it the prompt, the frog hates the clean rabbit. Okay, so the frog hates there it is. Okay, the frog hates the clean rabbit. The rabbit, okay, in this case here it says the rabbit admires a poor frog. Okay, what's going to happen actually when this thing finally converges? When you say with GigaTurtle, the frog hates the clean rabbit, and then actually it will repeat back stuff from the corpus, which is pretty remarkable. You'll see that ultimately it'll wind up doing that when we get conversions. So something really. So this is it. This is all there is to it. This is is pretty remarkable. Let's see what we have. The old rabbit. Okay, we can the dirty rabbit and Myers. Okay, we can start. We can check with that a bit more. But anyways, that's a demonstration of it. So I think maybe that's good enough for now to say that I mean, you're gonna in the recitation you're gonna kind of dig deeper into this, but all the pieces are there, so you can breakpoint stuff and you can watch stuff, and you can kind of really, if you have any, if anybody sits there and says, Michael, your lecture, in the lecture notes was a little bit vague, right? Say, well, okay, the code isn't. Let's go into the code. You got questions? Look at the code. See, this is it. That's the beauty of this this ethos of code as truth, is that you can go in there and you can, it's not ambiguous. It's like it's 100% clear. So, all right, good. Okay, so now let's go back to lecture. Okay, so we've looked at GPTs. Kind of got exposed to the idea, and so like the question might be like, what's the big deal? Okay, it is a big deal. This is what they call a result, and results, when they come along, you can't really decide when they come along, but they do come along. And this one came along 2017 and then beyond. That 2017, 18, 19. It was in that period. This is where this kind of got figured out. So. First of all, they're very general, so they can represent not just text, but audio, images, video. We're going to focus on text in this course. So, according to Karpathy, the way he puts it, he says, well, it's a general purpose trainable computer. Okay. So it's expressive in the forward pass. So it can capture, especially with the number of layers it is, it can capture lots of nuance. I mean, there's a lot of we know this. And then it's also optimizable. So it's like, so it's all kind of based on just the simple back prop, propagate the errors backward. Then we have a gradient, and then follow that gradient to minimize loss. It's remarkably efficient because it's all parallel, right? So the fact that we're doing all these things in batch, the fact that we're doing all this training simultaneously over a single example, all of that is that. I mean, if we're doing it as a recurrent network, then it's not so parallelizable. Things get kind of stretched out. The attention is all you need paper, I think, makes a really good case for this. I mean, if you look at the way it talks about the scalability, and also the fact that any in the context of window size, any token can talk to another token in just one kind of operation because of the way they're all listening on different queries, and they're all giving out things on different keys and passing values. So it's all kind of simultaneously in parallel. All that communication is happening. So that's the message passing. A really key point that it doesn't work. If you ablate this, you'll lose everything. And that's this notion of these residuals, this using addition and doing the residual connections. So that actually is one of the fundamental insights that came out of, I think, Microsoft research in Beijing. The folks there, the residual. I have to look and see, but the residual connection was like really an aha toward getting this off the ground. So then another thing is, I should look at it the following way. So this is what residuals give us. It's that because you have the residuals that are just kind of passing the signal forward without any kind of messing with the stuff that's coming from the transformer blocks, in the beginning of training, what happens is that you have a very, very direct way to pass back. You don't have a gradient problem. You don't have a vanishing gradient or exploding gradient problem, because you can pass, all the signal gets passed mostly back through the residuals, right? Because those are just always on, always just copying up. So what happens in the very beginning is that the transformer blocks are really just kind of adding just noise to the system. They're just kind of a big distraction. But what happens is as you do more and more training, what happens is these transformer blocks start kicking in. They start kicking in and then contributing, doing their own representation learning, and start kicking in their effects into the process. And so that's how, once you start really kind of moving toward getting like lost down, it starts really kind of picking up on things. So that's just really kind of a magical aspect of it with the residuals. Another reason why it's a big deal is because it hasn't really changed. It's like it's basically been pretty stable over the last 8 years. So therefore, that tells us that it's fundamental, that there's something very fundamental about it. So yeah, so now there's been a lot of optimizations to it. There's been a lot of thing that we'll talk about later in the course. But the core algorithm is really there's something fundamental with this. So this is a result. Okay, so what I want to do now, just to kind of like get it all kind of packaged up before lecture next week, is I want to just kind of finish up talking about tokenization because we kind of glossed that. So with tokenization, so traditionally, tokenization was based on words, right? So you could like just kind of split things up by the space or so. The NLT key is a natural language toolkit in Python was a real. I use that. It's pretty good. And space, I've used Spacey too. These things kind of you can manage kind of large dictionaries, but the problem with representing things tokenization via words is the dreaded out of vocabulary problem, right? So, and then also there's other things like for instance, for instance, like proper names, like my last name is not in the dictionary. Okay, so how are we going to represent that? And it's like there's lots of like very inelegant ways to kind of look at that. So it's not good to do tokenization based on words. All right, you can do it character based. Okay, so you can just have like, okay, these are the characters, ASCII. But the problem with that is then the meanings have a harder time to emerge. I mean, we have LOVE versus love. Love is like, if they have that as a separate token, then we have a better chances to do inferences off of that. Okay, so you could maybe we could talk about morphology or something from linguistics, but actually the solution pretty much universally adopted now is what's called byte pair encoding, BPE. Okay, and that's we're gonna show some code for that right now, so you guys can get some. We're gonna first talk about it, and then we're gonna show some code. One thing that's come up in my own work that I just want to kind of mention because I don't think people talk about it so much is the notion of a domain-based tokenizations. So a lot of times what you have when you're working with databases, you'll have what I would call a whole token. So for instance, an address. That somebody wrote that in there somewhere. That there's that's an address that somebody wrote into some field somewhere. If you can tokenize it, but if somebody points and clicks and they say, they point and click a query and they use that in the query, it would be nice if it can kind of grab that whole token and then be able to point to that exact value in the database. So that is something, like if you try to get this based on subtokens, it winds up being kind of hard to manage actually. So it's useful in like point and click query builders and maybe some other places as well. So, but anyways, let's focus on byte pair encoding because that's what everybody uses in the LLM world. Okay, so byte pair encoding. So it's all industrial LLMs use this. So here's the basic point behind it: is you take the basic characters, like you start out with all the characters. Those are all going to be tokens. Each of the individual characters are going to wind up being a token in the vocabulary. Okay, so what that means then is it means that we're going to have M, I, N, O, C, and K as characters. So if you need to encode my last name, you can do it by just stringing those tokens in a sequence. Okay, so you can pretty much cover the dreaded out of vocabulary problem is gone, all right? Because you can always just use the characters to spell whatever you want, and also then it deals with like misspellings. There's a lot of things that come along with that if you can just have the individual characters. However, what we want to do then is we want to extend it by the frequent subword tokens. So if we look in the thing, we'll see this in action when we run it. Okay, so we're going to learn this over a patch of text or over a sample. And then we're going to encode the text via a character level greedy encoder. And then we're going to decode via simple lookup. And but the lookup is a little tricky because you have to always try when you're doing a lookup. You always have to start with the largest tokens first and see if they match because you want to be greedy about it. All right. That's and we'll see that. Okay, so let's nose down into this code here, and I'm just going to move it over. So this is part of the code of the See if I can move it there. It's bpe.py, and it comes along with, let's see here. Does this work? Yeah, that works. It comes along with our TurtleGPT. Oops. Maybe I'll move this over here. And then I'll move this here. Uh-oh. I think I lost it. All right, one sec here. I'm going to pause. Okay, guys. Okay, so sorry about that. Now, what I've done is I've restarted this, and now we can actually watch this thing in action here. So what we're doing here is this is when we actually instantiate the corpus. This is where we're going to do the BPE, the byte pair encoding. So what happens here? So the first thing we do, we have data here. What is data? All right, data is, oh, look at that. There's the data, the clean from, okay, this is like that data that we had from before, right? So this is our data. So we're going to use this to sample the language to determine what are the most frequent, frequently occurring pairs or triples or etc. So we'll see how this goes. Okay, so the very first thing we do is we get the characters. So these are all the unique characters in the data set right there, chars. There's only 28 of them, but these are the characters, okay? And if you see here, where we have some special ones like the pound, the dollar sign, these are going to be reserved characters, the period, and then we have all these other ones. We have a capital A, capital T, etc. So there's 28 of those. But what we want to say is a vocabulary size. We're just mandating that we have a vocabulary size of 100. So those 100 here. So now we have, so we're going to start this out. So now we have token to integer. So what does T to I do? T to I is going to wind up doing self. There's only 28 so far. That's the token to integer. So basically it says that so for instance, if we want to encode an A, let's use a 6. All right, so this is just turning these into actual numbers. If we want to use an E, we'll turn that into a 10. Okay, so, and those are going to be index positions into the embedding matrix later on. But okay, that may be a bit too much information. And then we do it this way, then we're going to do it the opposite way as well. So that is if we get something out that has like, okay, the token 7, 14, 9, we have to go the inverse way and then pull out the tokens for those. And that is the I to T. And I to T right now starts out with I to T then basically is, okay, what if I give you something 6, then basically what should you print out? You should print out a little a, lowercase a. Right. Okay, so we have a vocabulary size, it's 100. And so what we're going to do then is we're going to do the BPE train sample. Okay. So what this is going to do, this is going to pull out just like from the data, it's going to pull out 1,000 characters. So the BP, this is what we're going to actually do the BPE over to kind of keep it a little bit like a subset of the thing. Where is it? BPE train. There you are. No. BPT train sample. 1,000. Oh, I'm sorry. This was just kind of telling us. It's like what's smaller, like 1,000 or the length of the data. So we only want to have 1,000 in the BPE train, but we'll see how that's just going to grab the first. I believe the first right there. Yeah. So the words. Right. Okay. So far, how many merges do we have to do? We still have 72 merges left to do. The words are going to be, we're going to basically go to the sample out to 1,000 places here, and we're going to like split them. We're going to like form a whole bunch of words here. We're going to pull a whole bunch of words in from the corpus here, and those words are going to wind up being, well, there they all are, right? So the words, we've just split them based on underscore. So the words there's 209 of them. So here are all the words. They're just kind of like, there they all are. Okay, there are repeats though. There are repeats of the words. Okay, so then what we do is we, right. for j in the number of merges. So here we're doing the first merge. Okay, the pairs, we're going to get the stats from the workspace. And this actually goes down into our BPE code here. So what this is going to wind up doing is this is going to just generate in our workspace. And what is a workspace? Here's a workspace. Our workspace right now is really pretty simple. It just basically tells us how often are these things occurring here. Okay, so we have 8 rabbits in there. And then, okay, so you'll kind of see how this works in a second here. So getting the stats. Okay, so let's just go up here so we can see. So these are the pairs. Okay, so just doing an analysis here, what we see here in the pairs, let's look at the pairs. There are 50 E's followed by this. Now, when I use the AE there, that means a space. So there are 50 times, when we look at all those words we have, there are 50 times that we have a word that's ending with an E and then a space. Okay. And then what do we have here? We have, oh, look there. 31 times we have OG. Okay. Probably in frog. I'm thinking. And dog. Frog and dog. Both. Okay, maybe it's another one. I don't know. Anyways. Okay. Right. And then, okay, so then there it is right there. Okay, so those are all like the pairs given the workspace. We're going to see that the workspace is going to be kind of merged. It's going to get merged together. We're going to apply these merges over there. Okay, so what's the best one? Okay, the best one is the E followed by the space there. So now what we do is we work that into the workspace, so that kind of gets it'll change the workspace around a little bit. And then notice right here what we're doing here. We're basically saying that whatever the I is, and we're going to walk I up to 100, it's going to basically set the text, the token to integer. It's going to put that to the best. So basically, once we do this, we now have finally. Okay, so now let's look at what we have for the integer to token. We look at that. We'll see how this thing's growing. So integer to token, where are you? You're under self. Integer to token now is 29 long. So look at this, the integer to token. So those are all the characters up front, and now we have this one little kind of the E with a space on it. So now we don't have to. When we do the encoding, if we see that, an E with a space, we can use this token rather than 2 tokens that are earlier in the list. I mean, instead of representing it with a 10 and a, where's a, okay, let me just go through this here, because I think if we did, I didn't want to do that. I wanted to actually have it so it stopped. Okay, we're going to have to rerun the thing. Darn it. Right, okay. Workspace, best. Okay, let's see what this is doing. No, we don't want it that way. We want to have it right here. Okay, let's go a couple spaces in. Okay, now let's look what's going on with our integer in the self here. If we look at the integer to token, now we'll see. Look here. We already have 31 at the with a space at the end of it. Oh, and then we also have bit, probably part of rabbit. Bit is 36 here, right? And then the with a lowercase t. Okay, so what we're doing here, though, let's go all the way to the end, and then we'll see the actual vocabulary that we actually build, like our byte pair encoded vocabulary that we built. And then what that's going to wind, look at it, here it is. We've got a full dog in there. So if you come across dog now, represent it as a 45, don't represent it as an individual D and O and a G, right? So as long as when you do the encoding, you walk this list from the longest to the shortest, you'll be doing it in a greedy way, a greedy encoding. And then when you do the decoding, you just kind of squirt them out, right? It's just based on the integers. So Yeah, so I think this might kind of give you a sense of like how it's done. Um, so I'm actually kind of proud of this because when I went out to like the literature, like you know, a lot of like implementations out there, by they were like really complicated. So a lot of times, what you'll see, I just want to make this as a side point. What you'll see sometimes is that okay, so one of the ideas behind Turtle is that we want to do this in straight. Okay, we're using Torch. Okay, fine. We're using CUDA. Okay, there's just some things you kind of some compromises. But what you don't when you work with this stuff, you don't want to get pulled into somebody's ecosystem play, right? You want to be able to kind of like. So there was something I saw one of the byte coder like examples out there, and it was like kind of you supposed to like to kind of understand it. You're supposed to connect to like something in OpenAI's like ecosystem. I mean, I'm no offense against OpenAI, but I was probably like I pulled this out, just like no, get away, get away, get away. Let's just kind of get this thing under a microscope. So the BPE actually was some effort to pull it. I can't remember how. Maybe there were pieces I grabbed it. Anyways, kind of keep it. This is like the whole point here though is to make these things as simple as possible. And on that note, I think I might work Turtle a little more this afternoon before I let it go to you guys. But BPE and Turtle and all this, all this code you see here is going to get released in the recitation, and you have some problems to do over that to kind of play around with it. So hope it's fun. Okay, guys, that's that then. That's the end of the lecture.